Good evening, and welcome back to the Dimensional Space Channel. Tonight, we explore a single, gentle question. One that sounds simple at first, and then slowly reveals itself to be one of the strangest puzzles in all of space travel. How long could a starship actually survive out there, alone, in the deep dark between two stars? Not a spaceship in a movie. Not something with glowing engines and dramatic music. A real machine. Metal, wiring, fuel, memory, all of it built by human hands, and then sent out into a void so vast that our entire solar system would look like a single grain of sand tossed into an ocean with no shore. We are not just asking about distance tonight, though the distance alone is staggering enough to make your mind go quiet with wonder. We are asking about time. Years, decades, perhaps centuries. We are asking what happens to metal, to circuits, to fuel, to memory itself, when it is left to drift through an environment that seems, in a strange way, almost designed to wear everything down to nothing. Consider this, just for a moment before we go further. Out there, a single grain of dust, smaller than a grain of sand, moving at only a small fraction of the speed of light, can strike a spacecraft with the force of a bullet. Cosmic radiation, invisible and relentless, slowly breaks down metal and circuitry at the atomic level, one quiet collision at a time. Seals that once held pressure and warmth begin to crack, slowly, from the inside out, like an old rubber gasket left in a drawer for 50 years. And that, quiet as it sounds, is only the beginning of what a true starship would face on a real crossing between the stars. We already have some hints. Real hints. Every spacecraft humanity has ever built and sent into the deep dark has quietly, patiently, been answering this question for us, whether we meant to ask it or not. Their power has faded. Their metal has aged. Their signals have grown fainter and fainter, like a voice calling from farther and farther away, until finally, softly, there is nothing left to hear. So tonight, we will follow that trail of clues. We'll drift out past the orbit of Neptune, out past the edge of the sun's influence, and into the true blackness beyond. We'll talk about the machines already out there right now, tonight, as you listen to this. We will talk about radiation and dust and the strange slow chemistry of decay in a vacuum. And we'll talk about what a real, honest-to-goodness interstellar starship, something built specifically to survive a journey between two stars, might actually endure. And I promise you this, the real answer is stranger, and in some ways far more beautiful than anything science fiction has ever prepared you for. But before we get into the science, let's just sit with the feeling of it for a moment. Let's understand why this question matters at all, and why, if you let it, it can become one of the most calming thoughts you take with you into sleep tonight. Think about the last time you tried to imagine truly, truly being alone. Not lonely in a sad way, just alone. In the way a lighthouse is alone on a rocky coast at 3 a.m, quietly doing its job while the rest of the world sleeps. Now imagine that feeling stretched out across trillions of miles. No coastline, no ocean, no air to carry a sound, not even the sound of your own voice. Just a small machine, tumbling gently forward, carrying a memory of home it will never return to. There is something strangely comforting in that image, isn't there? Not frightening. Comforting, because that little machine, whatever becomes of it, whatever slowly gives way to time and radiation and the endless patient erosion of deep space, will have done something almost nobody else in the universe, as far as we know, has ever done. It will have carried a small piece of a living, thinking civilization out into the dark, farther than any of us will ever personally go. And in a way, understanding how long it can survive out there is understanding something about endurance itself, about how a small, fragile thing, whether it's a spacecraft, or a memory, or a quiet thought drifting through your mind as you fall asleep, can last far longer than you might expect, if it's built carefully, and if it's given just enough shelter from the storm. So let your shoulders relax, let your breathing slow, and let's begin gently, the way any good bedtime story should, with the very first machines humanity ever sent out past the edge of everything familiar. Let's start close to home, in a strange way, even though close out here means billions of miles. Right now, tonight, as you lie there listening, there are a small handful of human-made machines that have crossed a boundary most of us never think about. They have left the region of space where the sun's solar wind holds sway and entered what scientists quietly call interstellar space. Not science fiction. Real. Right now. The most famous of these travelers are a pair of spacecraft called Voyager 1 and Voyager 2. They were launched in the late summer and early autumn of 1977, which means that by the time you're hearing this, they have been flying for roughly 5 decades. 5 decades of constant, silent motion through the dark. Voyager 1 crossed into interstellar space in 2012. Voyager 2 followed in 2018. And both of them are still, even now, sending back faint whispers of data to Earth. Using transmitters weaker than a household light bulb, across a distance so vast that their signals, traveling at the speed of light, take more than 20 hours to reach us. Sit with that for a moment. 20 hours. Light itself, the fastest thing in the universe, needs the better part of a day just to cross the gap between that little spacecraft and our own front porch. And yet, somehow, faintly, patiently, the message still arrives. Now here is where our story really begins, because Voyager wasn't built to last forever. No spacecraft is. It was built with a very specific, very human constraint in mind: power. Voyager doesn't have solar panels, because out where it's traveling, sunlight is far too weak and thin to be useful. It's like trying to warm your hands by the glow of a candle across a football field. Instead, Voyager carries something called a radioisotope thermoelectric generator, which is a wonderfully technical name for a beautifully simple idea. Inside, a small amount of a radioactive material, plutonium-238, slowly decays. As it decays, it releases heat. And that heat is quietly converted into electricity. The catch, the same catch every candle faces, is that this process fades over time. The plutonium doesn't stop producing heat suddenly. It fades gently, predictably, losing about 1% of its power roughly every 4 years. Slow and steady, like a fire burning low and orange through the night rather than snuffing itself out all at once. Because of this slow fade, mission engineers have had to make quiet, careful choices over the decades. One by one, instruments on Voyager have been switched off, not because they broke, but because there simply wasn't enough power left to run everything at once. It's a bit like a person on a long, long hike, gently setting down items from their backpack one at a time. Not because the items are useless, but because carrying everything all the way to the end simply isn't possible anymore. By the early 2030s, and this is not a guess so much as a careful, patient calculation by engineers who understand exactly how fast that plutonium is fading, Voyager will likely no longer have enough electricity to power even a single instrument. Its heaters will fail, its transmitter will grow quiet, and the spacecraft, still intact, still traveling, will become something else entirely. Not broken, not destroyed, simply silent. And here's the truly wonderful, almost dreamlike part of this. Even after Voyager falls silent, even after we can no longer hear from it, it will keep traveling. Forever. More or less. There's no air resistance in deep space to slow it down. There's no friction. Once an object like Voyager is moving through that vast emptiness, it keeps moving at the same steady speed, essentially without end, unless something happens to it. So already, in this first quiet clue, we learn something important about our bedtime question tonight. A spacecraft's death, if we can even call it that, doesn't usually look like an explosion or a catastrophic failure. It looks like a candle burning down. Slow, predictable, gentle, and even after the light goes out, the object itself, the physical body of the machine, can go on drifting through the dark for a very, very long time indeed. But Voyager and its slightly older sibling missions, Pioneer 10 and Pioneer 11, teach us more than just lessons about power. They also teach us about the deep, patient wear of the environment itself. Because power fading gently is one story. But there's another, quieter story happening at the same time, written not in electricity, but in the very atoms of the spacecraft's own metal and plastic and glass. And to understand that story, we need to talk about radiation. Not in an alarming way, in a slow, curious way, the way you might examine an old photograph left out in the sun for years, noticing how the colors have softly faded. Here on Earth, we're wrapped in a kind of invisible blanket. Our planet's magnetic field, along with our thick, generous atmosphere, quietly deflects and absorbs the vast majority of harmful radiation that comes streaming in from space. We rarely think about this shield, in the same way you rarely think about the walls of your own house while you sleep. It's simply there, doing its job, night after night, asking nothing of you in return. A starship traveling through deep space has no such blanket, none at all. Out there, radiation comes from several different quiet sources, each with its own personality, so to speak. There's radiation from the sun itself, though this fades the farther a spacecraft travels away from it. There's radiation from other stars scattered throughout the galaxy. And then there's something far stranger and far more persistent, galactic cosmic rays. Galactic cosmic rays are, in a sense, some of the oldest travelers in the universe. Many of them were flung outward by the deaths of massive stars, some in explosions called supernovae, sometimes long, long before our solar system even existed. They travel at extraordinary speeds, close to the speed of light itself, and they arrive from every direction, constantly, like a light and endless rain that never stops falling. Most of these particles are incredibly small, protons mostly, along with some heavier atomic nuclei. But what they lack in size, they make up for in speed and persistence. When one of these particles strikes a solid object, say a metal panel on a spacecraft, or a length of copper wiring, or a delicate silicon computer chip, it doesn't simply bounce off harmlessly. It can knock atoms out of place. It can break chemical bonds. It can, in very specific and very rare cases, flip a single bit of computer memory from a 0 to a 1, or a 1 to a 0, causing a tiny, almost invisible error deep inside a spacecraft's electronic brain. Engineers have a very fitting name for this. They call it a single event upset. And it happens more often than you might think, even to the spacecraft orbiting Earth today, let alone the ones drifting far out in interstellar space, where there's no planetary shield left at all. Now, one single cosmic ray strike isn't going to destroy a starship. Think of it more like a single drop of rain landing on a stone. Nothing happens from just one drop. But deep space missions aren't measured in single drops. They're measured in years, decades, potentially centuries of exposure. And over that kind of time, drop by drop, quietly, patiently, the rain begins to leave its mark on the stone. Metal, believe it or not, actually becomes slightly brittle after prolonged exposure to this kind of radiation. It's a process engineers sometimes describe using the term radiation embrittlement. On a molecular level, the constant bombardment gradually shifts the internal structure of certain metals and alloys, making them just slightly less flexible, just slightly more prone to cracking under stress than they were when they first left Earth. Plastics and rubber seals suffer in a similar, though different, way. Many polymers rely on long chains of molecules linked together, a bit like an enormously long strand of pearls. Radiation can snap those chains, or cause unwanted new links to form between them, gradually changing the material's properties. A seal that was once flexible and pliable might, after enough decades of quiet radiation exposure, become stiff or brittle, or prone to hairline cracks. And once a seal begins to crack, even slightly, it can allow tiny amounts of gas to leak out, or allow the vacuum of space to creep in where it shouldn't. And then there's the electronics, which are, in many ways, the most vulnerable part of any starship, because computer chips rely on extraordinarily precise, almost impossibly small structures, features sometimes just a few dozen atoms wide. Cosmic radiation, over enough time, can degrade these delicate structures. Some spacecraft electronics are specially hardened against radiation, built with thicker, more resilient designs specifically to survive this kind of long exposure. But even hardened electronics have their limits, especially across a journey lasting not years, but potentially generations. There's a beautifully strange irony hidden in all of this, and it's worth pausing on for a moment. Radiation, in small controlled doses, is something we generally think of as invisible, harmless, easy to ignore. And for a short trip, say a journey to the moon or even to Mars, it mostly is fairly manageable, at least for the spacecraft's hardware, even if it poses real concerns for any human crew aboard. But stretch that same journey out across years and decades, out into true interstellar distances, and that quiet. Invisible rain becomes one of the single greatest challenges facing the long-term survival of any starship. It's the kind of decay you'd never notice happening in the moment. No dramatic flash, no warning light, no sound at all, of course, since sound can't travel through a vacuum anyway. Just a slow, patient, accumulating erosion, the same way a stone in a riverbed is shaped, ever so slowly, by water that never seems to be doing anything dramatic at all, and yet, given enough time, can carve entire canyons. And radiation, as slow and quiet as it is, isn't even the most physically dramatic threat facing a starship out there. For that, we need to talk about something that sounds almost too strange to be true. We need to talk about dust. Picture, for a moment, a single grain of dust. Not a large one. Something closer to the size of a grain of flour, or perhaps even smaller. closer to the width of a human hair. On Earth, a speck this size is almost meaningless. It floats through a sunbeam in your living room. You'd brush it off your sleeve without a second thought. Now imagine that same tiny grain moving at several tens of thousands of miles per hour. Some interstellar dust and the small rocky or icy fragments scattered throughout the space between stars can move at truly extraordinary speeds relative to a passing spacecraft, sometimes tens of kilometers per second, occasionally even faster, depending on the relative motion between the dust and the ship. At those speeds, even something as small and seemingly insignificant as a single grain of dust carries a surprising amount of kinetic energy, because kinetic energy depends not just on an object's size, but on the square of its speed. Double the speed, and you don't just double the impact, you quadruple it. And at the speeds we're talking about here, that tiny grain, weighing next to nothing, can strike a spacecraft's hull with an impact roughly comparable to a bullet fired from a gun. This is not an exaggeration for dramatic effect, by the way, though I understand if it sounds like one. Spacecraft engineers take this threat extremely seriously, and they have for decades. The International Space Station, for instance, orbiting far closer to Earth than any interstellar mission ever would, still has to account for exactly this kind of danger, and it uses specialized multi-layer shielding, sometimes called Whipple shields, named after the astronomer who first proposed the idea to protect against these tiny high-speed impacts. A Whipple shield works on a wonderfully clever, almost gentle principle. Rather than trying to stop a fast-moving particle with one single thick, heavy wall, which would be enormously impractical to build and to launch, engineers instead use several thinner layers, spaced some distance apart. When a tiny particle strikes the outer layer, it doesn't simply punch through cleanly. It shatters, along with a portion of that outer layer, into a small, expanding cloud of debris. That cloud spreads out as it travels toward the inner layers, so that by the time it reaches them, its energy is spread across a much wider area, dramatically reducing the chance of a serious, penetrating breach. It's a bit like the difference between being struck by a single hard pebble versus being gently sprinkled with a small handful of sand. Same total material, roughly speaking, but spread out, softened, made survivable. Now, out in true interstellar space, far beyond the reach of any planet's protective environment, the dust is generally far less dense than the debris found closer to a busy planet like Earth. Space, even interstellar space, is not quite the chaotic hailstorm sometimes imagined in movies. Most of the time, the space between the stars is remarkably, almost eerily empty. A starship could travel for a very long time indeed without encountering anything larger than the tiniest, faintest speck of dust. But very long time is precisely the scale we're discussing tonight. And even a low probability event, spread out across centuries of travel, spread out across trillions upon trillions of miles, starts to become a near certainty rather than a rare exception. It's a bit like flipping a coin. Any single flip landing on heads 20 times in a row is wildly unlikely. But if you flip that coin often enough, for long enough, eventually it happens, purely because of how much time and how many attempts you've allowed for. Interstellar dust also comes in a few different, quietly fascinating varieties. Some of it is leftover material from the vast clouds of gas and dust that stars and planets are born from, sometimes called the interstellar medium, drifting slowly through the galaxy on timescales of millions of years. Some of it comes from the tails and debris fields of comets, or from collisions between asteroids flung outward over unimaginably long stretches of time. And in truly rare cases, a starship might even encounter what scientists sometimes call rogue objects, small icy or rocky bodies that were ejected from their home star system entirely, and now drift alone through the vast emptiness between the stars, much like our starship itself. The good news, and there is good news here, is that engineers already understand a great deal about how to protect against this kind of threat, precisely because we've had to think carefully about it for missions much closer to home. A genuine interstellar starship, if humanity ever builds one, would almost certainly be designed with dedicated shielding at its leading edge. The surface facing directly into the direction of travel, since that's the side that would encounter the overwhelming majority of any dust or debris. Some engineers and physicists studying interstellar travel have even proposed carrying a physical shield ahead of the main spacecraft, sometimes envisioned as a thick disk of ice or dense material, sacrificed slowly over the course of the journey, absorbing impacts so the more delicate parts of the ship, tucked safely behind it, remain untouched. It's not so different, in spirit, from a person walking into a storm holding an umbrella slightly ahead of themselves, letting the umbrella take the brunt of the rain so they can stay dry underneath. So dust, like radiation, isn't the kind of threat that ends a mission all at once, in one dramatic instant. It's a threat that accumulates, small impact after small impact, across years, across decades, slowly pitting and weakening the outer surfaces of a starship, the same way wind and sand slowly smooth and reshape a desert rock over the course of centuries. And now that we've talked about radiation attacking a starship from the inside out and dust attacking it from the outside in, there's a third quiet threat we need to consider. One that has nothing to do with impacts or particles at all. It has to do with something far more basic, and in some ways, far more human. It has to do with heat and the strange, patient challenge of temperature in the vacuum of space. Here's a small, gentle paradox worth sitting with for a moment. Space is famously cold. We've all heard that phrase, or something close to it, since childhood. And it's true, in a sense. The background temperature of the universe itself, the faint leftover warmth from the Big Bang, sits at a mere few degrees above absolute zero, the coldest temperature theoretically possible. But here's the paradox. Space itself doesn't have a temperature in quite the same way a room does, because temperature, as we normally experience it, depends on countless tiny particles bumping into each other, transferring heat through direct contact. And space, especially the space between the stars, is almost entirely empty. There's nothing there to bump into. No air. No water. Nothing to carry heat away from an object through simple contact, the way a cold breeze carries heat away from your skin on a winter night. This means a starship doesn't lose heat the way you or I do. It can only lose heat through a much slower, quieter process called radiation, where warmth escapes as invisible infrared light, drifting gently outward into space, whether or not anything is there to receive it. This creates a strange and delicate balancing act for spacecraft engineers. A ship traveling toward a star will be gently warmed by sunlight on the side facing that star, while the opposite side, facing away, radiates its heat outward into the cold and receives almost nothing in return. This means one side of a spacecraft can be remarkably warm, while the other side, just a few meters away, drifts far colder, sometimes with a difference of hundreds of degrees between the sunlit face and the shadowed one. And a starship traveling through true interstellar space, far from the gentle warmth of any star at all, faces an entirely different problem. Almost no external heat source whatsoever. Out there, in the space between stars, an unpowered, unheated object would, given enough time, slowly settle toward that same extremely cold background temperature, just a few degrees above absolute zero. Now, a starship carrying its own power source, like the radioisotope generator we talked about with Voyager, or perhaps a more advanced system on a hypothetical future starship, can generate its own warmth internally, keeping its most delicate components, its electronics, its fuel lines, its sensitive instruments, within a survivable temperature range. But this creates yet another quiet, patient challenge, because generating heat requires power, and power, as we've already learned, fades over time. There's also a more subtle issue at play here, something engineers call thermal cycling. Even with careful, stable internal heating, a spacecraft rarely experiences a perfectly constant, unchanging temperature throughout its entire structure. Different components heat and cool at slightly different rates, especially during maneuvers or as a ship's orientation shifts, or as internal systems switch on and off to conserve power. This creates tiny, repeated expansions and contractions in metal, in solder joints, in the delicate connections between electronic components. It's a bit like slowly bending a paperclip back and forth. The first few times, nothing seems to happen at all. The metal simply flexes and returns to its original shape. But bend it enough times, across enough cycles, and eventually, quietly, a fracture begins to form, right at the point of repeated stress, until finally, the metal breaks. Solder joints on circuit boards are especially vulnerable to this kind of slow fatigue. Across years or decades of gentle thermal cycling, tiny cracks can develop in these joints, potentially breaking an electrical connection that once worked perfectly well. This is one of the quiet, patient reasons engineers building long-duration spacecraft go to such extraordinary lengths in testing their hardware here on Earth first, deliberately cycling components through repeated heating and cooling, thousands of times over, trying to uncover these weaknesses long before a real starship is ever launched into the dark. And there's one more thing worth mentioning here. Something that connects the cold of space to a much more familiar, almost cozy idea. Many of the fluids and lubricants that keep a spacecraft's moving parts working smoothly, valves, gears, small motors, can behave very differently at extremely low temperatures than they do here on Earth. Some lubricants become thick and sluggish in extreme cold, almost like honey left in a refrigerator. Others can become brittle, losing their ability to properly coat and protect moving surfaces at all. This is one of the quiet reasons spacecraft engineers spend so much careful effort selecting exactly the right materials for a given mission. Sometimes choosing lubricants that remain functional across an enormous range of temperatures, or designing systems that minimize the number of moving parts altogether, since a part that doesn't need to move is a part that can't seize up, or crack, or fail from the cold. So already, in just these first few threads of our story tonight, radiation, dust, and temperature, we can start to see a pattern forming. None of these threats are sudden. None of them are dramatic. At least not in the way a meteor strike in a movie might be dramatic, with sparks and alarms and shouting. They're all slow, patient, quiet, the kind of forces that work not in seconds, but in years, wearing away at a starship's hardware, one small, gentle increment at a time. And that pattern, that quiet, patient wearing down, brings us to perhaps the most important resource of all for any long-duration starship. Not fuel, not shielding, but power itself, and the question of how, exactly, a machine could keep itself alive for decades or centuries in a place with no sunlight, no fuel stations, and no way at all to ask for help. Let's talk about power, because in many ways, power is the true heartbeat of any starship. Everything else, the heaters keeping equipment warm, the transmitters sending signals home, the instruments gathering data, all of it depends on having enough electricity to function. And out in deep space, generating that electricity is a wonderfully tricky problem. Solar panels, the most familiar power source for spacecraft close to Earth, become almost useless the farther a ship travels from its home star. Sunlight intensity fades according to what's called the inverse square law, meaning that if you double your distance from the sun, you don't receive half the sunlight, you receive a quarter of it. Triple the distance, and you're down to just a ninth. By the time a spacecraft reaches the outer edges of our own solar system, sunlight has already grown so faint that solar panels large enough to matter would need to be impractically enormous. And in true interstellar space, far from any star at all, solar power simply isn't an option, because there's no sunlight there to collect in the first place. This is why missions like Voyager and the New Horizons spacecraft that gave us our first close look at Pluto rely instead on those radioisotope thermoelectric generators we mentioned earlier. Slow, steady, radioactive decay, quietly producing heat, quietly converted to electricity for years and years on end, without needing any sunlight at all. But even this remarkably reliable power source has its limits, tied directly to the physics of radioactive decay itself. Every radioactive material has what's called a half-life, the amount of time it takes for half of the material to decay into something else. Plutonium-238, the fuel used in most modern radioisotope generators, has a half-life of roughly 87 years. This means that after 87 years, only half of the original plutonium remains, still producing heat. After another 87 years, only a quarter remains. And so on, fading gently, gradually, forever, but never quite reaching zero. The same way a cup of hot coffee left on a table cools down and down, approaching room temperature, without ever quite freezing. For a mission like Voyager, launched with a certain amount of plutonium fuel, this steady, predictable fade means the spacecraft's usable power output shrinks a little more with each passing year, until eventually, there simply isn't enough electricity left to power even a single instrument, let alone a heater or a transmitter. Now, here's where things get quietly fascinating. When we start imagining a genuine interstellar starship, something built specifically for a journey between two stars, rather than a mission like Voyager, which was really designed to explore our own solar system and only happened to keep going afterward. A dedicated interstellar starship might use a much larger radioisotope generator, carrying more fuel from the very beginning, extending its usable lifetime considerably. Or it might use an entirely different power source altogether. Some proposed designs imagine small, carefully controlled nuclear fission reactors, similar in principle to the nuclear power plants we use here on Earth, but scaled down and adapted for the unique demands of deep space travel. A fission reactor could, in theory, provide considerably more power for a considerably longer period than a simple radioisotope generator, though it introduces its own set of engineering challenges, particularly around safely managing nuclear fuel and radioactive waste across a journey lasting decades or longer. Other, more speculative concepts imagine that a future starship might not carry its own fuel at all, but might instead be propelled and powered by energy beamed from home, using enormous laser arrays or similar technology based back in our own solar system, pushing the starship forward and potentially providing power as well, at least for a portion of the journey, before the beam grows too faint across the vast distance to remain useful. Each of these approaches to power comes with its own particular timeline, its own particular way of fading, gently, over the years. But they all share one thing in common with poor aging Voyager. None of them last forever. All of them, eventually, quietly run out. And this is where our bedtime question starts to reveal its first truly interesting layer, because survival for a starship doesn't have one single definition. There are actually several different, quietly overlapping answers to the question of how long a starship could survive, depending on exactly what we mean by survive. Does the starship's structure remain intact, drifting silently through space? That might last for an extraordinarily long time indeed, potentially millions of years, since there's very little in the deep vacuum of interstellar space capable of breaking apart a solid metal object entirely, especially once its power and instruments have already gone quiet. Does the starship remain capable of communicating with Earth? That timeline is considerably shorter, tied directly to how much power it carries and how quickly that power fades. Does the starship remain capable of completing its original mission, gathering new scientific data, adjusting its own course, making decisions? That timeline might be shorter still, since even a small failure in one critical system, one specific circuit, one specific sensor, could end a mission's usefulness long before the spacecraft's structure or power source has fully given out. So really, when we ask how long a starship could survive, we're asking at least three quietly different questions, layered one inside another, like a set of nesting dolls. And each answer, it turns out, unfolds on a wildly different time scale. Let's gently unpack each of those three layers, one at a time, the way you might slowly unwrap a series of gifts, each one revealing something a little different from the last. The first layer, the simplest one in some ways, is structural survival. Simply put, does the physical body of the starship remain whole rather than breaking apart into fragments? This, it turns out, might be the layer with the longest timeline of all, by an enormous margin. Once a spacecraft's engines have stopped firing, once it's simply drifting through the vast emptiness of interstellar space, there's remarkably little out there capable of destroying it entirely. No wind to erode it, the way wind slowly erodes a mountain here on Earth. No water to rust it, since rust requires oxygen and moisture, both of which are essentially absent in deep space. No bacteria, no fungus, none of the countless small biological processes that slowly break down objects left out here on our own planet. The greatest threats to structural integrity, as we discussed earlier, are radiation slowly making certain materials more brittle over time, and the occasional impact from dust or small debris. But both of these processes are remarkably slow, especially once you account for just how empty interstellar space really is. Some scientists estimate that a solid metal object, drifting undisturbed through interstellar space, could potentially remain structurally recognizable for hundreds of thousands, or even millions of years, gradually pitted and worn by radiation and dust, but never fully destroyed. The same way ancient stone monuments here on Earth, weathered by wind and rain for thousands of years, remain recognizably intact even after all that time. Of course, recognizably intact doesn't mean unchanged. Over such enormous timescales, a starship's outer surface would likely become gradually pitted, its paint or protective coatings slowly stripped away by countless microscopic impacts, its more delicate external components, antennas, sensors, solar panels, potentially becoming brittle enough to eventually crack or break off entirely. But the core structure, the main body, the thick metal frame, could genuinely persist for a staggeringly long time, quietly drifting through the galaxy long after every living person who remembers building it has been gone. That's our first layer. Now, let's gently move to the second. How long can a starship remain capable of communicating with home? This timeline is considerably shorter, and it's tied directly to that steady, patient fade of power we discussed earlier. A starship's transmitter needs electricity to function, and as that available power gradually shrinks year after year, there eventually comes a point where there simply isn't enough electricity remaining to power the transmitter at all. No matter how efficiently the rest of the ship conserves its resources. For Voyager, this timeline appears to be roughly 5 to 6 decades from launch, give or take a few years depending on exactly how mission engineers choose to manage the remaining power as it fades. For a hypothetical dedicated interstellar starship carrying a larger power source specifically designed for a longer journey, this timeline might reasonably stretch to a century, or perhaps even several centuries, depending on the exact size and type of power source used. But there's a second, quieter factor limiting communication, beyond power alone, distance itself, and the strange way a spacecraft's radio signal gradually weakens the farther it travels from Earth. Radio waves, like all forms of light, spread outward from their source, gradually growing fainter and fainter as they travel, following that same inverse square law we mentioned earlier with sunlight. By the time Voyager's faint radio signal reaches Earth today, after traveling more than 20 hours at the speed of light, it arrives so incredibly weak that receiving it at all requires some of the largest, most sensitive radio antennas ever built by humanity. Listening with extraordinary patience for a whisper of a signal buried deep within the natural background noise of the universe itself. A genuine interstellar starship, traveling not merely to the edge of our solar system but across the vast gulf toward another star entirely, would face this same challenge, but multiplied enormously. The nearest star system to our own, a trio of stars called Alpha Centauri, sits over 4 light-years away. That means even a signal traveling at the speed of light, the fastest possible speed in the entire universe, would take more than 4 years just to make the one-way trip back to Earth. And by that point, the signal would have grown so extraordinarily faint that receiving it at all would require power, antenna technology, and patient listening far beyond anything currently in use today. So even if a starship's power source and internal systems remained perfectly healthy for centuries, there would eventually come a point, based purely on the mathematics of distance and signal strength, where meaningful two-way communication with Earth becomes extraordinarily difficult, or perhaps impossible altogether, unless our own technology for listening continues to improve considerably over that same span of time. And this brings us gently to the third layer, the shortest and, in many ways, the most fragile timeline of the three. How long can a starship remain capable of completing its original mission, gathering meaningful new data, and functioning as the fully capable scientific instrument it was originally designed and launched to be. This is where all of our earlier threats, radiation, dust impacts, thermal cycling, slowly compound together, quietly stacking up over the years. A single critical sensor failing, damaged perhaps by a single unlucky dust impact, or perhaps by the slow accumulated effect of decades of radiation exposure, could end a mission's core scientific usefulness long before its power runs out entirely, and long before its physical structure begins to break down. This is why real spacecraft missions are so often designed with redundancy in mind, meaning multiple backup systems capable of taking over if a primary system fails. Voyager, for instance, carries backup computers, and mission engineers on Earth have, more than once across the decades, had to creatively reprogram the spacecraft's remaining functional systems to compensate for components that failed along the way. It's a bit like a resourceful traveler on an extremely long journey, gradually adapting and improvising as certain tools break or wear out, relying more and more on cleverness and careful planning as the trip stretches on. A dedicated interstellar starship, if humanity ever builds one for a genuine journey to another star, would almost certainly be designed with this exact philosophy in mind from the very beginning. Multiple redundant systems, careful shielding for the most critical components, perhaps even the ability to self-repair certain issues automatically, without needing to wait years for instructions to arrive from Earth, since a round-trip conversation, a question sent and an answer received, could take years, or even decades, depending on how far the ship has already traveled. So when we ask, gently, how long could a starship survive out there, we find that the honest answer depends entirely on which survival we mean. Structurally, potentially millions of years. Able to communicate, perhaps a century or several centuries, depending on its power source and how patiently we listen. Able to complete its full original mission, gathering fresh, meaningful data the whole way. Perhaps only a matter of decades, limited by the slow, quiet compounding of all the threats we've discussed tonight. 3 different answers to what seemed, at the very start of this story, like one simple question. Let's pause here for a moment and drift gently back to those early pioneers, quite literally, because there's something tender and worth lingering on in the story of the Pioneer spacecraft. The 2 missions that came even before Voyager. Pioneer 10 launched in 1972, and Pioneer 11 followed in 1973. Both of them, like Voyager after them, eventually crossed the boundary out past the outer planets and into the deeper reaches of our solar system. Pioneer 10's last faint signal was received back on Earth in 2003, more than 3 decades after launch, its power finally too weak to transmit any further. Pioneer 11 fell silent even earlier, in 1995. But here's the tender part. Both Pioneer spacecraft carry a small gold anodized plaque bolted to their frames, engraved with a simple message intended for anyone, or anything, that might one day encounter them, drifting silently through the galaxy. The plaque shows the figures of a man and a woman, a simple diagram of our solar system with Earth marked clearly, and a map showing the position of our sun relative to several distinctive pulsars, stars that emit extremely regular, clock-like pulses of radiation which could theoretically help any future finder calculate exactly when, and from where, this little message was sent. It's a beautifully hopeful gesture, in a way, especially when you consider the odds involved. Space, even within our own galaxy, is so enormously vast and empty that the chance of Pioneer 10 or 11 ever actually drifting close enough to another star system for anyone or anything to notice them at all is almost unimaginably small. And yet, the plaques were included anyway. Not because anyone genuinely expected them to be found and read anytime soon, but because there was something quietly meaningful in the act of sending a message outward, regardless of whether anyone might ever receive it. Voyager took this idea even further, carrying what's often called the golden record, a phonograph record containing sounds and images meant to represent the breadth of life and culture on Earth. Music from different cultures and eras, greetings spoken in dozens of different languages, natural sounds like wind, rain, and birdsong, even a recording of a human heartbeat, all of it etched onto a golden disc, bolted to the side of a spacecraft that will likely outlast every other physical trace of our civilization, drifting silently through the galaxy for millions of years after every building we've ever built has crumbled back into dust. There's something wonderfully calming, I think, in sitting with that image as you drift off tonight. A small golden record, carrying a human heartbeat, traveling forever through the vast, quiet dark, long after everything else about us has faded away. Now, all of these missions, Pioneer and Voyager alike, were never truly designed as dedicated interstellar starships. They were built to explore our own solar system, its planets and moons, and their journey beyond that out into true interstellar space happened almost as a bonus, a natural continuation of a path they were already following. This means their design, their shielding, their power systems weren't specifically optimized for the unique challenges of a genuine multi-decade or multi-century interstellar crossing. A true, dedicated interstellar starship, something built from the very beginning with the specific goal of reaching another star system, would look quite different. And this is where our story starts to gently drift from what we already know, from real spacecraft with real measured data, into the realm of careful, thoughtful speculation, grounded in real physics and real engineering, but imagining machines that don't quite exist yet. Several serious research efforts over the decades have quietly explored exactly what such a starship might look like. One notable example is a concept called Project Daedalus, studied by the British Interplanetary Society in the 1970s, imagining a robotic starship propelled by a series of small nuclear fusion explosions, gradually accelerating the craft to a meaningful fraction of the speed of light before coasting the remainder of its journey toward a nearby star system. More recently, a research initiative called Breakthrough Starshot has explored an entirely different approach, imagining swarms of extremely small, lightweight probes, each attached to a thin, reflective sail, pushed forward not by rockets at all, but by the gentle, steady pressure of powerful lasers based here in our own solar system, potentially accelerating these tiny probes to a significant fraction of light speed within just a few minutes, before releasing them to coast, unpowered, for the remainder of a journey that might still take 20 years or more to reach a nearby star system like Alpha Centauri. Each of these concepts, wonderfully different in their approach, share one thing in common with the question we're gently exploring tonight. They all have to grapple with exactly the same quiet, patient threats we've discussed: radiation, dust impacts, the steady fade of onboard power, thermal cycling. And each concept proposes its own particular solutions, its own particular trade-offs, its own particular answer to how long exactly their imagined starship could realistically be expected to survive and function across such an enormous journey. Let's take a gentle moment here to talk about speed and why it matters so deeply to our story tonight. Perhaps more than almost anything else we've discussed so far, the distances between stars are so enormous that the speed a starship travels doesn't just affect how quickly it arrives. It fundamentally changes how long its various systems need to survive in the first place, and even, in a strange and wonderful way, how time itself is experienced aboard the ship. Let's start with something familiar. Voyager, our fastest, farthest human-made object, travels at roughly 38,000 miles per hour relative to the Sun. That sounds remarkably fast, and it is, by any everyday human standard. And yet, at that speed, it would still take Voyager more than 70,000 years to travel the same distance separating us from Alpha Centauri, our nearest stellar neighbor. If it happened to be pointed in that direction at all, which, as it happens, it isn't. 70,000 years is an almost incomprehensibly long span of time, especially when you remember that Voyager's power source will likely be depleted within just a handful of decades from now. Its transmitter will fall silent long before it's even a meaningful fraction of the way to another star system. This is precisely why serious interstellar starship concepts focus so heavily on finding ways to travel dramatically faster than anything we've launched so far. Concepts like Project Daedalus imagined reaching perhaps 12% of the speed of light. Breakthrough Starshot imagines its tiny probes reaching perhaps 20% of light speed. At 20% of light speed, a journey to Alpha Centauri might take a little over 20 years rather than tens of thousands. And this changes our entire question, doesn't it? A starship's various systems, its power source, its shielding, its electronics, only need to survive long enough to complete the specific journey being asked of them. A starship traveling at a meaningful fraction of light speed toward a nearby star might only need its critical systems to function reliably for a few decades, which, as we've discussed, is well within the realm of what current radioisotope generators and radiation-hardened electronics can plausibly achieve, especially with careful, generous engineering margins built in from the very beginning. But here's where things get quietly, wonderfully strange, and worth savoring slowly as you drift towards sleep. At speeds approaching a significant fraction of the speed of light, time itself begins to behave in an unusual way, at least from certain perspectives. This is a genuine, well-established consequence of Einstein's theory of relativity, called time dilation. Here's the gentle version, without diving too deeply into complicated mathematics. The faster an object travels, relative to an observer who is, comparatively, standing still, the slower time appears to pass for that fast-moving object, at least from the still observer's point of view. This isn't a trick of measurement or perception. It's a genuine, physical difference in how time itself unfolds, confirmed repeatedly through careful scientific experiments here on Earth, and even through the small, measurable time differences experienced by astronauts who spend extended periods aboard the International Space Station, traveling at considerable speed relative to those of us on the ground. For a starship traveling at 20% of light speed, this effect would still be fairly modest, a small fraction of a percent difference between time as experienced aboard the ship and time as experienced back on Earth. But for more speculative, far more advanced starship concepts, ones capable of reaching 50, 70, even 90% of light speed, the effect becomes dramatically more pronounced. At 90% of the speed of light, for instance, time aboard a starship would pass at less than half the rate experienced back on Earth. A journey that takes, say, 10 years, according to instruments and observers back home, might feel to the ship itself and to anything experiencing time aboard it like only about 4 or 5 years had passed. This means quietly and remarkably that a sufficiently fast starship's own onboard clock, so to speak, including the slow, patient decay of any radioactive power source or the gradual thermal cycling of its components, would genuinely tick more slowly, from an outside observer's point of view, than the same processes happening back on Earth. The ship, in a very real physical sense, would be aging more slowly than the years passing back home. Now, this doesn't mean radiation damage or dust impacts happen any less severely from the ship's own local perspective. Aboard the ship itself, everything would feel entirely normal, with radiation and dust impacts occurring at their usual rate, exactly as expected. But from Earth's perspective, watching that same ship from a great distance, its entire aging process, including the systems we've spent this whole story discussing, would appear to unfold more slowly than a simple calculation based on ordinary, everyday physics might suggest. It's a beautifully strange thought to sit with, isn't it? That a starship traveling fast enough, far enough, could in a sense quietly outrun a portion of its own aging process, at least as measured by those of us watching from home, not defeating time entirely, simply experiencing it a little differently, the way two people can walk the same path at different paces and arrive having felt the journey pass by in subtly different ways. Let's drift now toward a gentler, more hopeful thread in our story, because so far we've talked mostly about decay, about wear, about the slow, patient erosion of a starship's systems over time. But engineers, quietly, thoughtfully, have also spent decades imagining ways a starship might resist that decay, or even, in a very real sense, heal itself along the way. The simplest and most time-tested approach is redundancy, something we touched on briefly earlier. Rather than relying on a single critical component to perform an essential function, engineers design multiple backup systems, so that if one fails, another can quietly take over. Voyager itself carries backup computers and backup instruments, precisely because engineers, even back in the 1970s, understood that a journey of this length would inevitably involve some components failing along the way. A dedicated interstellar starship would almost certainly take this philosophy considerably further. Imagine not just one or two backup systems, but entire redundant sets of critical components, perhaps physically separated from one another within the ship's structure, so that a single unlucky dust impact striking one small area of the ship couldn't disable multiple backup systems at once. Beyond simple redundancy, engineers have also proposed more active forms of self-repair. Some concepts imagine small robotic systems aboard the starship itself, capable of physically inspecting and repairing certain components, replacing a failed part with a spare, or rerouting electrical connections around a damaged section of circuitry, all without needing to wait for instructions from Earth, since, as we discussed, a round-trip message to Earth and back could take years, or even decades, depending on how far the ship has traveled. This idea of onboard self-sufficiency becomes especially important when we consider that a genuine interstellar starship might need to make its own decisions, quietly, autonomously, without any real-time guidance from home at all. If a critical system begins to fail, and Earth is years away by radio signal, the ship itself, or some sufficiently advanced onboard computer system, would need to recognize the problem and respond entirely on its own. This is one of the quiet reasons some researchers studying interstellar travel have proposed that a future starship might carry what's sometimes called an onboard artificial intelligence system, not in the dramatic movie sense of a computer suddenly becoming self-aware, but simply as a sophisticated, carefully designed system capable of monitoring the ship's health, diagnosing problems, and making sensible engineering decisions. The same kind of decisions a team of human engineers back on Earth might make, if only they had the luxury of being present in person. Now, all of this discussion so far has assumed a starship without any human crew aboard. Simply a robotic explorer sent outward to gather data and, perhaps, quietly report back for as long as it's able. But there's another, quite different category of interstellar starship worth mentioning gently here. One that brings an entirely new and fascinating set of considerations. The idea of a generation ship. A generation ship imagines something altogether different from a small robotic probe. It imagines a genuinely enormous vessel, carrying an entire community of people, potentially numbering in the hundreds or thousands, who would spend their entire lives aboard the ship, with their children and their children's children, eventually completing the journey to another star system many generations after the original crew first departed Earth. This idea introduces threats and challenges entirely separate from anything we've discussed so far tonight, because now we're not simply asking how long metal and electronics can survive, but how long an entire self-sustaining human society, with its own food production, its own air and water recycling, its own social and psychological well-being, could remain healthy and functional across a journey that might last centuries. We won't dive too deeply into the details of generation ships tonight, since that's really a story for another quiet evening entirely. But it's worth pausing to notice how the question shifts entirely once human lives, rather than robotic components, are the primary concern. A generation ship's designers would need to think not just about radiation shielding for computer chips, but radiation shielding thick and comprehensive enough to protect fragile human bodies across an entire lifetime, or several lifetimes, of exposure. Not just about power sources lasting decades, but power and life support systems reliable enough to sustain human life for potentially hundreds of years, without a single catastrophic failure. It's a beautifully sobering thought, in its own gentle way, that the question we're exploring tonight, how long can a starship survive, takes on an entirely different weight and meaning, depending on whether we're asking about a small robotic explorer quietly drifting and reporting back for as long as it's able, or an entire floating civilization carrying human hopes and human lives across the vast gulf between the stars. Let's return gently to the small, quiet details of materials science for a while, because there's a particular kind of comfort in the specifics, in understanding exactly what a starship might be made of, and exactly how each material responds to the long, patient pressures of deep space. Spacecraft engineers have spent decades carefully studying which materials hold up best under the unique combination of stresses we've discussed tonight: radiation, extreme temperature swings, the vacuum of space itself, and the occasional high-speed impact from dust or debris. Aluminum alloys are commonly used in spacecraft construction, prized for being lightweight yet strong, an important consideration when every single kilogram of a spacecraft's mass adds enormous cost and complexity to actually launching it from Earth in the first place. But pure aluminum, on its own, isn't particularly resistant to the specific kind of radiation damage we've discussed. So engineers often blend it with small amounts of other metals, like copper or magnesium, creating alloys with improved resistance to both radiation and the general fatigue caused by thermal cycling. Titanium, meanwhile, offers remarkable strength and impressive resistance to fatigue, making it a popular choice for certain structural components, particularly ones that need to withstand repeated stress over very long periods. It's more expensive and somewhat heavier than aluminum, but for the components where long-term durability matters most, that trade-off is often well worth it. For the truly critical outer layers, the parts of a starship most directly exposed to both radiation and dust impacts, engineers sometimes turn to more specialized materials entirely. Certain ceramic composites, for instance, offer excellent resistance to the extreme heat generated by a high-speed impact, since when a fast-moving dust particle strikes a solid surface, the sudden, intense energy of that collision can generate a small but genuinely significant burst of heat, sometimes enough to briefly vaporize a tiny portion of both the incoming particle and the surface it strikes. Then there are the various coatings applied to the outside of many spacecraft, thin layers designed to reflect excess heat or to provide a small amount of additional protection against radiation. Multi-layer insulation, a material you might recognize from photographs of spacecraft. That shiny gold or silver, almost crinkled-looking outer layer is actually made of many extremely thin sheets of material, often a plastic film coated with a very thin layer of metal, layered together with small gaps of vacuum or minimal density material between each sheet. This clever, delicate layering works a bit like the fluffy softness of a warm winter blanket, trapping small pockets of near vacuum between each thin layer, which dramatically reduces how quickly heat can escape or enter the spacecraft through simple radiation, since heat has to cross many small gaps, each one slowing its passage rather than moving freely through a single solid material. Circuit boards and electronic components, meanwhile, are often protected using specialized radiation-hardened designs, sometimes involving thicker layers of certain materials specifically chosen to absorb or deflect incoming radiation before it can reach the most delicate, most vulnerable parts of a computer chip. Some spacecraft even use older, simpler electronic designs deliberately, rather than the newest, most advanced chips available, precisely because older designs with larger, sturdier internal structures tend to be considerably more resistant to radiation damage than the newest chips, which pack an enormous number of extremely small, extremely delicate features into a tiny space. There's something quietly poetic in that particular trade-off, isn't there? That sometimes, for the specific purpose of surviving decades in deep space, older and simpler genuinely outperforms newer and more advanced, precisely because simplicity itself can be a form of resilience. Seals and gaskets, meanwhile, the small rubber or polymer components responsible for keeping air pressure contained within certain compartments, or keeping fuel safely sealed within its tanks, are often made from specialized synthetic materials engineered specifically to resist the embrittlement caused by both radiation and extreme cold. Even so, these seals remain in many ways one of the more vulnerable components on any long-duration spacecraft, precisely because they rely on maintaining a very particular, delicate balance of flexibility, a balance that naturally tends to degrade, slowly and quietly, given enough time. This is one of the quiet reasons some more advanced Starship concepts propose minimizing the use of pressurized compartments and moving seals altogether wherever possible, favoring instead solid-state components with no moving parts and no need for pressure seals at all, since a component that doesn't need to move and doesn't need to hold a seal is a component that simply cannot fail in quite the same way. All of this careful, patient material science, gathered across decades of real spacecraft missions and careful laboratory testing, forms the quiet foundation for any serious attempt to imagine a genuine interstellar starship. Not glamorous, not dramatic, but absolutely essential. The same way the quiet, careful choice of insulation in your own home's walls matters far more to your comfort on a cold night than almost anything else, even though you likely never think about it at all. Let's take a moment here, a quiet little detour, to bring some of these numbers down to a more human scale, because it's easy for figures like millions of years or 20% of the speed of light to simply wash over you, sounding impressive without actually meaning very much. Consider this. If Voyager 1 continues drifting at its current speed, and somehow, against wildly improbable odds, happen to be heading directly toward a particular nearby star called Gliese 445, it would arrive there in roughly 40,000 years. 40,000 years ago, human beings hadn't yet invented writing. We hadn't yet built the pyramids. We were still, in a broad sense, quietly figuring out agriculture. And Voyager, still faithfully drifting along at the same steady pace, would only just be arriving at its destination. There's something almost comical about that, in a gentle, cosmic sort of way. It's a bit like packing a very slow, very patient lunch to bring on a walk, only to realize the walk itself is going to take longer than the entire history of human civilization. You'd want a very good sandwich indeed. And yet, this comparison also reveals something important about why speed matters so profoundly to any real interstellar mission. The difference between traveling at Voyager's speed and traveling at, say, 20% of the speed of light isn't simply a modest improvement, the way upgrading from a bicycle to a car is a modest improvement. It's the difference between a journey lasting tens of thousands of years, longer than the whole of recorded human history, and a journey lasting a single human generation. Something a person setting out from Earth might, with enough luck and enough good engineering behind them, live to see completed. This is precisely why so much of the serious research into interstellar travel focuses so heavily and so patiently on finding practical ways to dramatically increase a starship's speed, because that single factor, more than almost any other, determines whether a mission's various systems even need to survive for a plausible, human-relatable span of time at all, or whether they'd need to somehow endure for a length of time so vast it starts to lose any real meaning to us. Let's also gently compare our Starship's challenges to something a little closer to home, something perhaps sitting in your own kitchen right now. Think about a simple household battery, the kind you might put in a flashlight or a remote control. Left sitting unused on a shelf for several years, that battery will slowly lose some of its charge, even without ever being used, through a natural process called self-discharge. It's the same basic principle behind Voyager's slowly fading plutonium, just operating on an enormously different scale, and over an enormously different span of time. Or think about an old rubber band, left forgotten in a drawer for a decade or two. When you finally find it again, it's often gone brittle, snapping the moment you try to stretch it, rather than flexing the way it once did when it was new. That's a small, everyday, kitchen drawer version of exactly the same radiation and temperature-driven embrittlement we discussed happening to a starship's seals and gaskets. just accelerated by ordinary air and ordinary time here on Earth, rather than by cosmic rays and interstellar cold. There's something quietly comforting, I think, in recognizing that the challenges facing a starship, however exotic and futuristic they might sound, are really just larger, slower, more patient versions of processes happening all around us, all the time, in our own everyday lives. The universe doesn't reserve its patient, gradual decay only for spacecraft traveling between the stars. It applies the very same gentle, unhurried processes to the rubber bands in our drawers, the batteries on our shelves, the old photographs slowly fading in a box in the attic. Perhaps that's part of why this question feels so soothing to sit with tonight, rather than unsettling. Decay, out there among the stars, isn't some strange alien process, foreign to everything we know. It's the same familiar, patient unwinding we witness all around us here at home, simply stretched out across distances and timescales large enough to make our minds go pleasantly, quietly still. Let's drift now toward the very far edge of this question, the almost unimaginable timescales where even our patient, careful physics starts to blur into something closer to poetry. Suppose, just for tonight's sake, that a starship's power has long since faded, its transmitter silent for longer than human civilization has existed. Suppose its instruments stopped gathering data before anyone alive today was even born. What happens to it then? What happens across the truly vast stretches of time that follow? For a very, very long while, on the order of many millions of years, the starship would simply continue drifting, slowly, quietly, gradually being worn down by the same gentle, patient forces we've discussed tonight. Radiation would continue its slow work, making certain metals a little more brittle with each passing millennium. Occasional dust impacts, rare but inevitable given enough time, would continue to gently pit and reshape its outer surface. Very, very slowly, the starship's more delicate external features, its antenna, perhaps, or any thin external plating, might eventually crack away entirely, drifting off separately into the dark, while the main body continues onward, alone, given an unimaginably long enough span of time, tens of millions of years, perhaps hundreds of millions. Even the toughest metals would eventually be worn down by this continuous, patient bombardment, gradually eroding, gradually thinning, the same way a mountain range, given enough hundreds of millions of years, is eventually worn down into gentle hills, and then, eventually, into nothing more than sediment scattered across a plain. But here's where the time scale becomes so vast that it starts to fold back into something almost too abstract to picture clearly. On these kinds of scales, other things are happening too, not just to the tiny drifting starship, but to the wider universe around it. Stars are born and die. Galaxies slowly drift and occasionally, gently, collide with one another over spans of time so long that even a starship enduring for 100 million years would represent only the faintest, briefest flicker within that much larger cosmic story. It's a strange, quiet thought to hold in your mind as you drift towards sleep tonight, that a small machine, built by human hands, launched from a small blue planet, could, in principle, outlast every single trace of the civilization that built it, outlast our language, our cities, our very species perhaps, and still, after all of that, only represent a small early chapter in the far longer story the universe is left to tell. And yet, for all of that vastness, for all of those millions upon millions of years, our original bedtime question tonight, the truly meaningful one, was never really about eternity. It was about something a little more human, a little more relatable, a little more comforting. It was about how long a starship could remain functional, useful, capable of teaching us something new, capable of still, in some small way, being a living connection back to the people who built it and sent it on its way. And it's here, gathering together everything we've gently explored tonight: radiation and its slow, patient erosion, dust and its bullet-like impacts, the steady fade of onboard power, the strange stretching of time itself at extraordinary speeds, that we arrive, finally, at the heart of tonight's story. The real, honest answer to the question we began with. Before we drift onward to the end of our story, let's pause for one more gentle detour, because there's a wonderfully strange thread here worth pulling on. One that connects everything we've discussed tonight to a much bigger, much older mystery. If a starship, once its power fades and its systems fall quiet, can continue drifting largely intact for hundreds of thousands, or even millions of years, then it stands to reason that other civilizations, if they exist anywhere else in our galaxy, might have already sent out their own quiet, patient explorers long before humanity even existed. And if that's true, some of those ancient, silent starships might, even now, still be drifting somewhere out there among the stars, their power long since exhausted, their builders perhaps long since gone, and yet their physical structure, patiently, quietly, still intact. This isn't idle speculation, by the way. It's a genuine thread of scientific curiosity that astronomers have taken quite seriously in recent years, especially following one particularly strange event back in 2017. When astronomers detected an object passing through our own solar system that had clearly come from somewhere else entirely, from beyond our own sun's gravitational reach altogether. This object was given the name Oumuamua, a word borrowed from the Hawaiian language, roughly meaning a messenger from afar arriving first, chosen because it was discovered using a telescope in Hawaii. And Oumuamua turned out to be genuinely puzzling, in a quiet, thoughtful way rather than a dramatic one. It was unusually elongated, tumbling end over end as it moved, and it showed a very slight, unexpected acceleration as it left our solar system. A tiny extra push that didn't quite match what gravity alone would predict. Now, the overwhelming scientific consensus, based on careful patient analysis, suggests Oumuamua was very likely a natural object, perhaps a peculiar fragment of ice and rock, shaped by unusual processes we don't yet fully understand, with that small extra acceleration possibly explained by gently venting gas, similar to how a comet behaves, even though Oumuamua didn't show the more obvious glowing tail we typically associate with comets. But its strangeness did prompt a few careful scientists to gently ask the question we've been exploring tonight, just from a different angle. If an ancient, artificial starship, built by some long-vanished civilization elsewhere in the galaxy, had drifted silently through interstellar space for millions of years, its power and instruments long since faded into silence, what would it actually look like if it happened to pass through our own solar system today? Would we even be able to tell the difference between a strange natural object and an ancient, silent, artificial one? Given how similarly worn and weathered both might appear after such an enormous span of time, it's an important, humbling question, precisely because everything we've discussed tonight about slow, patient decay applies just as much to a hypothetical alien starship as it does to our own. After millions of years of quiet drifting, exposed to the same radiation, the same rare dust impacts, the same relentless cold, any artificial structure would likely become almost unrecognizable as anything built with purpose or intention. Its surfaces worn smooth or gently pitted, its more delicate features long since broken away, leaving behind perhaps only a simple, somewhat irregular shape, not unlike Oumuamua's own strange, elongated form. This thought connects, in a wonderfully quiet way, to a much older and more famous puzzle in astronomy, sometimes called the Fermi paradox, named after the physicist Enrico Fermi, who once posed a deceptively simple question during a casual lunchtime conversation with colleagues. Given the sheer size and age of our galaxy, and given how many billions of stars it contains, many of them considerably older than our own sun, shouldn't we expect to have encountered some clear evidence of other civilizations by now, whether through their radio signals, or their spacecraft, or some other unmistakable sign of their existence? One of the many gentle, thoughtful answers offered to this puzzle over the decades touches directly on everything we've explored together tonight. Perhaps other civilizations have indeed sent starships outward, just as we've begun to seriously consider doing ourselves. But perhaps, given the truly vast distances and the truly enormous timescales involved, any such starships would spend the overwhelming majority of their existence not as active, communicating explorers, but as silent, drifting objects. Their brief active lifespan of mere decades or centuries reduced to the faintest possible flicker, when measured against the millions of years they might continue existing afterward in complete silence. If that's true, then the reason we haven't obviously detected such objects isn't necessarily because they don't exist. It might simply be because we're looking for the wrong thing entirely. We might be listening for signals, when what's actually out there, drifting patiently through our own galactic neighborhood, are simply silent, weathered shapes, indistinguishable, at a casual glance, from any other small asteroid or icy fragment tumbling gently through the dark. There's something quietly humbling, and yet also strangely comforting, in that thought that the vast majority of any starship's existence, whether built by human hands or by some other civilization entirely, unfolds not in the exciting communicative phase we naturally focus on and imagine, but in this much longer, much quieter phase of simply persisting, existing, drifting onward, patiently, without any need to speak, or to be heard, or to be understood by anyone at all. Perhaps that's the truest, gentlest answer to tonight's question, layered one final time. A starship's most active, most exciting chapter, the one filled with data and discovery and careful communication back to the people who built it, is almost certainly the shortest chapter of its entire existence. And its longest chapter, by an enormous margin, is simply this: quiet, patient, undisturbed persistence, drifting through a vast and mostly empty dark, needing nothing at all from anyone, and asking nothing in return. There's one more quiet thread worth gently following before we return home, and it has less to do with metal and radiation, and more to do with the people who build these machines and then have to let them go. Think, for a moment, about what it must feel like to be one of the engineers who worked on Voyager back in the 1970s. A young person, fresh into their career, spending years carefully designing and testing a spacecraft, pouring their attention into every wire and every joint, knowing full well that this particular machine was built to travel far beyond anything humanity had attempted before. That same person, now, decades later, has likely spent their entire working life, and perhaps a good portion of their retirement too, quietly checking in on their old creation, reading the latest updates, watching its power slowly fade, exactly as the physics always predicted it would, feeling, perhaps, a strange kind of parental pride, watching this small, faithful machine outlive its own expected lifetime again and again, decade after decade, still faithfully sending its whispers home. There's a particular kind of patience required for this sort of work, one quite different from most careers. A bridge engineer sees their bridge completed within a few years and can walk across it themselves. A Voyager engineer builds something they know, from the very beginning, they may never see fully finish its journey, not in any meaningful sense, since Voyager's true journey, out past our solar system and into the deeper reaches of the galaxy, will continue long after every person who built it has passed on. And yet, they build it anyway, carefully, patiently, with the same quiet, steady dedication a person might bring to planting a garden or writing a letter meant to be opened by someone many years in the future. Not because they'll personally witness every outcome, but because the work itself, the careful, patient act of building something meant to endure, holds its own quiet meaning, regardless of whether they're present to see how the story eventually unfolds. Perhaps that's a small, gentle thought worth carrying with you tonight too, as your own day comes to its quiet close. That not every worthwhile thing needs to be finished, or witnessed, or fully understood by us personally, in order to matter. Sometimes, the most meaningful work is simply the careful, patient act of sending something good out into the world, and then, gently, letting it continue on its own way, trusting that it will keep going, quietly and faithfully, long after our own part in its story has ended. So, after everything we've gently traveled through tonight, what is the real answer? How long could a genuine interstellar starship actually survive out there, in the deep, quiet dark between two stars? Here it is, the quietly astonishing truth this whole journey has been leading toward. There isn't one answer. And that, strangely, is the answer itself. A starship doesn't have a single lifespan, the way a person has a single, roughly predictable number of years, or the way a flower has a single season of blooming before it fades. A starship, instead, dies many small, separate deaths, each one at its own pace, each one telling its own quiet story, layered one on top of another like sediment settling slowly at the bottom of a very old, very still lake. Its most fragile systems, certain sensors, certain exposed instruments, might succumb first. Perhaps within just years or a couple of decades, worn down by an unlucky combination of radiation and dust, or simply by the ordinary, patient fatigue of long use. Its ability to communicate, to send even the faintest whisper back to the people who built it, fades next, tied directly to the patient half-life of its onboard power source, lasting anywhere from a handful of decades, as with Voyager, to potentially a century or more, for a more advanced starship purpose built for a longer journey. Its ability to think, to compute, to make decisions, to adjust its own course or diagnose its own problems, might persist a while longer still, especially if its most critical electronics were carefully shielded and thoughtfully designed with generous redundancy from the very beginning. perhaps surviving in some limited minimal form even after its main transmitter has gone permanently quiet. And its physical body, its outer shell, its core structural frame, might persist longer than almost anything else about it, drifting silently through the galaxy for hundreds of thousands of years, perhaps millions, gradually worn and pitted by the same slow, patient forces we've spent this whole evening exploring, but never fully destroyed, not for an almost unimaginably long time. So when someone asks, simply, how long could a starship survive out there? The honest, complete answer is gently, quietly layered. It depends on which part of the starship you mean, and which part of surviving you're asking about. But here's the truly wonderful, almost tender insight hiding at the very center of this whole question. The one thing worth carrying with you, gently, into sleep tonight. A starship's death, unlike almost every kind of death we're familiar with here on Earth, isn't really an ending at all. Not in the usual sense. It's a gradual, gentle transformation from an active, functioning explorer, gathering data and sending it faithfully home, into a silent messenger, still moving, still intact, simply no longer speaking. And then, eventually, over a truly staggering span of time, from a silent messenger into something closer to a fossil, a quiet, physical record of a moment in time, drifting for eons through the same vast dark it once explored. At no point in that long, slow transformation does the starship simply disappear. It doesn't shatter, in most cases, or vanish, or dissolve, the way things so often do here on Earth, worn away by weather and bacteria and the countless small, hungry processes of decay we're surrounded by every day, out there, in the profound emptiness between the stars. Decay takes on an entirely different character, patient almost beyond imagining, gentle in its own strange way, and remarkably, comfortingly, incomplete, even after spans of time so long they make our own human lives feel like the briefest, quietest breath. And there's one more thread worth gently pulling here. One final piece of this puzzle that I think might be the most quietly moving part of the whole story. Every single spacecraft we've sent out there, Pioneer, Voyager, and someday perhaps a genuine dedicated starship built specifically for a journey between two stars, is already in its own way answering this question for us, right now. In real time, whether or not we're paying close attention. We don't actually need to imagine some distant, hypothetical future to understand how a starship ages and fades. We're watching it happen, quietly, patiently, right now, in the fading signals and slowly dimming power readings of spacecraft that have already been traveling for decades. Voyager isn't a thought experiment. It's a living, ongoing answer, unfolding one quiet year at a time, exactly as predicted by the same patient physics we've explored together tonight. And so, in a strange, gentle way, we already know quite a lot about what awaits a true interstellar starship, long before humanity ever builds and launches one specifically for that purpose. We know its power will fade, slowly, predictably, following the same patient mathematics of radioactive decay that governs Voyager's own dimming heartbeat today. We know radiation will slowly work at its metal and its circuits, the same quiet, invisible rain falling now on spacecraft already out there in the dark. We know dust, rare but inevitable, will eventually leave its small, bullet-like marks upon its hull. And we know that, even after all of that, even after every system has gone quiet, even after every light has faded, the starship itself, the physical, solid, tangible proof that a small group of curious, careful beings on a small blue planet, once reached outward into the dark, will likely still be there, drifting, intact, waiting, patiently, for absolutely nothing at all, and yet somehow, in its own quiet way, still complete. That, I think, is the quietly beautiful truth hiding inside tonight's question. Not that a starship survives forever, because nothing, not even the vast and patient universe itself, quite manages that. But that its ending, when it finally, gently arrives, isn't really an ending in the way we usually imagine one. It's simply a long, slow, graceful fading. From speaking, to listening only, to simply existing, quietly, for a very, very long time indeed. And somewhere in that slow, graceful fade, I think there's a small, comforting lesson for the rest of us too. Resting here on our small blue planet, in our warm beds, at the end of a long day. That endurance doesn't always look dramatic. It doesn't always announce itself with fireworks or fanfare. Sometimes, endurance simply looks like continuing, quietly, patiently, one gentle moment after another, long after anyone is watching closely enough to notice. Let's slow down even further now, and walk gently, decade by decade, through what a genuine interstellar mission might actually experience, from the very first moment of launch, all the way out into the deep, quiet unknown. Think of this as a kind of soft, unhurried timeline. Something to let your mind wander through as your body settles further into rest. Imagine, for a moment, a starship freshly launched from our own solar system, propelled by some combination of the technologies we've discussed tonight. Perhaps a powerful laser array pushing against a thin, reflective sail, gradually building speed over the first few days or weeks of its journey, before settling into a long, silent coast toward its destination. In the first year, everything is, relatively speaking, calm. The starship is still fairly close to home, still within the gentle, familiar reach of our own sun's light and warmth, even if that light has already grown considerably fainter than it appears here on Earth. Its instruments run smoothly. Its power source, freshly loaded with fuel, operates near its full original capacity. Engineers back on Earth receive regular, clear updates, the signal still strong enough to arrive without excessive delay. By the 5th year, the ship has traveled far enough that sunlight has become almost meaningless as a source of warmth or power, and the starship now relies entirely on its own internal systems to stay warm and functional. Radiation exposure, though still relatively modest at this stage, has begun its slow, patient work, and engineers monitoring the ship's health data might begin noticing tiny, gradual shifts in performance. Nothing dramatic, just the faintest early whispers of the where to come. By the 15th or 20th year, the ship has likely crossed into what we might think of as true interstellar space, far beyond the reach of any planetary or even stellar influence at all. Out here, it's now facing the full, unfiltered environment we've spent this evening exploring. The occasional micrometeoroid impact, the steady, invisible rain of galactic cosmic rays, and its onboard power source, whatever form it takes, has already begun its own slow, gentle fade. Following the familiar mathematics of radioactive half-life. By this point, mission engineers back on Earth, patient as ever, have likely already had to make some quiet, careful decisions, powering down certain non-essential instruments to preserve electricity for the ship's most critical systems. in exactly the same way real mission teams have done with Voyager across the decades. It's a bit like carefully rationing supplies partway through a very long expedition, not out of panic, but out of calm, thoughtful foresight. By the 40th or 50th year, if the Starship is approaching its destination, perhaps a nearby star system like Alpha Centauri, depending on its exact speed, its systems have likely weathered several decades of accumulated wear. Some components may have failed entirely by now, hopefully compensated for by the redundant backup systems built in from the very start. Its structure, meanwhile, remains largely intact, its outer surface perhaps a little more pitted and worn than the gleaming machine that first launched from Earth so many years earlier, but fundamentally sound. And then, if all has gone well, if the careful engineering and generous redundancy have done their patient work, the Starship arrives. It begins gathering entirely new kinds of data, perhaps images of planets orbiting a star other than our own, perhaps measurements of a whole new solar system's composition and structure, information that has never before been available to human science. Gathered firsthand, at last, after a journey lasting the better part of a human lifetime. This new data, gathered at the far end of such an extraordinary journey, would then need to make its own long trip home, traveling at the speed of light across those same 4+ light years, meaning that even after the ship itself has successfully completed its outward journey, the people back on Earth waiting to receive this precious new information would need to wait several more years, patiently, before the first images and measurements finally arrived. It's worth sitting with that thought for a moment, gently, because it reveals something quietly moving about the entire endeavor. Everyone involved in launching such a mission, the engineers, the scientists, the many careful hands that built and tested and launched the Starship, would very likely need to wait the better part of a human lifetime, decades upon decades, simply to receive the very first meaningful results. Many of the people who first proposed and designed such a mission might not even be alive to see its data arrive, and yet missions like this get proposed and studied, and in some early forms even begun, again and again throughout the history of space exploration. Because there's something in us, some deep, patient, curious part of the human spirit that finds this kind of long, uncertain wait not discouraging, but quietly worthwhile. The same spirit, in a smaller way, that leads someone to plant a tree they know they'll never see fully grown, simply because they understand, gently, that someone else will one day sit beneath its shade. A starship, then, isn't just a machine slowly aging and fading across the decades. It's also a kind of long, patient gift, sent forward through both space and time, from one generation to the ones that will follow, carrying with it not just scientific instruments and data, but a small, quiet piece of the curiosity and the hope of everyone who helped it on its way. Before we close tonight, let's take one last slow, gentle look upward, or at least, in your mind's eye, outward, into that vast dark we've been exploring together this whole evening. Right now, tonight, as your eyes grow heavy and your thoughts begin to soften and blur at the edges the way they do just before sleep finally arrives, there are real, physical machines drifting out there in the true interstellar dark. Voyager 1, farther from Earth than anything else humanity has ever built, moving steadily away from us at this very moment, its faint signal still, somehow, patiently reaching home. It has been traveling for nearly 50 years now. Its power continues its slow, familiar fade, and yet it persists, quietly, faithfully, doing exactly what it was built to do for just a little while longer, before it, too, eventually falls silent and begins that long, slow transformation from an active explorer into a silent, drifting messenger. There's a certain kind of peace, I think, in knowing that such patient, quiet endurance is possible, that something built by careful, curious hands, launched outward with hope, but without any real guarantee of success, can continue on, faithfully, for decades, simply by being well made and well cared for and given just enough shelter from the harshest parts of its environment. And perhaps, as you drift towards sleep tonight, there's a small, gentle comfort in applying that same thought a little closer to home, too. That you, like a small starship of your own, don't need to solve every problem all at once, or last forever without rest, or never encounter a single difficulty along your own path. You simply need enough shelter, enough care, enough steady, patient maintenance to keep going for just a little while longer, one quiet day at a time, the same way Voyager has kept going, one quiet year at a time, for nearly half a century now. The universe, it turns out, isn't quite the harsh, hostile place it's sometimes made out to be in more dramatic stories. It's patient. It's slow. It wears things down gently, gradually, rather than all at once. And in that patience, there's a strange, quiet kind of gentleness, even in the way it eventually, brings even the sturdiest starship's active life to a close. So tonight, as you finally let go and drift off, carry this thought with you if you'd like. Somewhere out there, farther than light itself can travel in less than a full day, a small, faithful machine continues onward, unhurried, uncomplaining, doing exactly what it was built to do. And it will likely keep doing so, in one form or another, structurally intact and quietly drifting, for far, far longer than any of us watching from home will ever be here to see. That's not a sad thought. It's a remarkably peaceful one, because it means that some small, careful part of human curiosity, human hope, human patience, is already out there, right now, safely tucked inside a small metal frame, drifting gently through the dark, entirely unbothered by the passage of time in the way that we, wrapped up in our short human lives, so often are. And if you find yourself, even now, half asleep, wondering what it might actually feel like to stand inside such a spacecraft, to look out through a small window and see nothing but scattered points of light in every direction, utterly still, utterly silent, you're not alone in that wondering. Almost everyone who studies these missions closely, at some point, quietly imagines the same thing. There's no shame in it. It's simply the natural, gentle pull of genuine wonder, the same pull that likely brought you here to listen tonight in the first place, and the same pull that will, one day, carry some small part of humanity a little farther out into that dark than we've ever managed before. And with that, gently, we come to the end of tonight's journey together. We began with a simple question. How long could a starship survive out there, alone, in the deep dark between two stars? And we found, I hope, that the real answer was never really about a single number at all. It was about layers, slowly unfolding, one after another. A few years for the most delicate instruments, a handful of decades for meaningful communication, perhaps a century or more for its deepest, most carefully shielded systems, and then, almost beyond imagining, hundreds of thousands of years, perhaps millions, for its patient, physical body to finally, slowly wear away into nothing at all. If you're still awake with me now, and I suspect, if I've done my job gently enough tonight, that fewer and fewer of you are, I hope you're carrying something soft and warm with you into sleep. Not facts to memorize, just a feeling, a quiet sense of scale and patience, and the strange, comforting knowledge that endurance, real endurance, rarely looks dramatic. It simply looks like continuing, softly, one more day, one more year, one more quiet orbit around an old and patient star. If tonight's journey helped your mind settle and your body finally relax into rest, I'd love for you to consider leaving a like on your way into sleep, or subscribing if you're new here and would like to drift off with us again tomorrow night. There's no rush, of course, no pressure at all. Just a small, quiet nudge, whenever you're ready, whenever it feels natural. Until next time, sleep well, drift gently, and remember that somewhere out there, right now, farther than light can easily reach, a small and faithful machine is still quietly making its way through the dark, exactly as it was built to do. Good night.